Welcome to the Deep Dive. We're here to cut through the noise and give you the essential insights on complex topics. And today, well, we're tackling something that honestly sounds straight out of science fiction. The idea that you could maybe build a time machine using an MRI scanner. And the sources we looked at, they hint at this really incredible possibility, right? Manipulating magnetic fields perfectly to make a system seem to snap back to how it was earlier. So our mission in this deep dive is to explore that fascinating, maybe frustrating line between what the math says is possible, this idea of time symmetry in physics equations, and what reality, thermodynamics and relativity actually allows, which seems to be time only moving forward.
Exactly. And that tension, that's what makes this whole area so interesting, I think. When you hear scientists talk about MRI, they use terms like phase reversal and echoes. It sounds like rewinding something. But we really need to clarify what's going on. Why can an MRI pull off this, frankly, amazing trick of local phase reversal, but it absolutely cannot turn back the clock in a, well, chronological sense? We need to get a handle on what phase reversal actually is and why it stays stuck in the quantum realm, basically.
Okay, let's start right there. The MRI itself. If we're even going to think about time reversal, we need to understand what this MRI echo thing really means.
Yeah.
Because, when I first heard the term echo, I pictured like sound bouncing off a pannion wall. It comes back later. It implies movement, travel. But that's not quite right here, is it?
No, not really. And the term echo is a bit misleading for that very reason. It makes you think of something reflecting off something else externally. But what we're actually seeing is the spontaneous reappearance, just for a moment, of a signal that had completely faded away. And this is done using a really clever technique called the spin echo sequence. So, first step, a 90-degree radio frequency pulse. Think of it like a little nudge. It tips the nuclear, spins the tiny magnets and atoms so they're aligned in the transverse plane, sort of spinning sideways. Okay, second step. Almost immediately, these spins start getting out of sync. They dephase. Why? Because the magnetic field isn't perfectly uniform everywhere. Each spin feels a slightly different field. So they start precessing or spinning at slightly different speeds.
Ah, okay. So they quickly drift apart. Their signals start canceling each other out, and poof, the overall signal we can measure just disappears.
That's exactly the signal loss. Now here comes the really clever part, the 180-degree pulse. It's timed precisely. It hits the spins after they've started dephasing, and it essentially flips them over, like completely inverts their orientation in that plane.
Flips them like pancakes. The fast ones become slow relative to the center, and the slow ones become fast.
Sort of. The ones that were spinning faster and getting ahead are now suddenly pointed in a direction where they're effectively behind the average, and the slower ones that were lagging are now effectively ahead. So over the next little time interval, what happens? The faster ones naturally catch up to the slower ones. And for one brief instant, bang! They all realign. They rephase perfectly for a moment.
And that perfect momentary alignment makes them all emit a signal in unison, a measurable burst of radio frequency energy.
Right.
And that's the echo.
Wow.
That's some serious precision engineering.
It really is phenomenal. But, and this is the crucial but, while the spins have momentarily got their act together relative to each other, they haven't actually traveled back in time. The whole system is still subject to decay processes governed by forward time equations. We call them the Bloch equations. That decay continues the whole time.
Wait a second, though. If they achieve perfect realignment, even for a microsecond, isn't that a kind of proof that the system did reverse itself, at least on that tiny scale? If I could perfectly put, say, spilled milk back in the bottle, is that reversing time for the mill?
That's where the math meets the messy reality. The Bloch equations, which describe how these spins behave, they actually have two main ways the signal decays, T and T. The clever 180-degree pulse, it undoes the T decay. TU is that loss of phase coherence, the spins getting out of sync with each other, but it can't do a thing about TU decay. TU is about the spins losing energy to their surroundings, to the lattice, as physicists say. It's thermal relaxation. And T decay, that loss of energy, is fundamentally irreversible. It's linked to entropy. So yes, you restore the phase alignment for a moment, you fix TU temporarily, but the overall energy keeps draining away. The overall disorder or entropy of the whole system keeps increasing. That's the thermodynamic arrow of time, and it's relentless.
I think I see. It's like,
Yeah.
okay, imagine you have a bunch of clocks that started perfectly synchronized, but they all run at slightly different speeds, so they drift apart. The 180 pulse is like a magic button that makes the fast clock suddenly run slow and the slow clocks run fast, so for a moment they all show the same time again. But the batteries in all the clocks are still running down, and the room they're in is still getting older. You've only reversed their relative drift, not the overall passage of time or energy loss.
That's a really good analogy, exactly. And this reversal we're talking about, it's happening entirely within the abstract realm of phase space. Think of phase space as a map showing all possible states, all the orientations and speeds of the spins. The 180 pulse reverses their trajectory on that map, but it doesn't physically push the system back along the timeline, back through actual space-time.
Okay. And this technique, this kind of manipulation, isn't just for hospital MRIs, right? This spin echo idea. It's actually related to some fundamental experiments physicists do, exploring time reversal in quantum systems, like something called the Loschmidt echo.
Yes, absolutely. The Loschmidt echo is a very closely related concept. It's often studied in nuclear magnetic resonance, or NMR, which is the sort of parent technology of MRI, usually in more controlled settings, like with ultra-cold atoms or very specific quantum systems. The name comes from Joseph Loschmidt, a 19th century physicist. He actually questioned whether the laws of physics required things to always get more disordered. He proposed a thought experiment about reversing particle velocities. So both the spin echo in MRI and the Loschmidt echo in NMR, they beautifully demonstrate that, mathematically speaking, the dephasing process can be reversed within a closed, controlled group of particles. They show the underlying quantum equations have this time symmetry built in if you can perform that reversing operation perfectly.
Right, if. So if you could somehow do it absolutely perfectly, keep everything totally isolated, could you essentially play the system's evolution forwards and backwards, like rewinding a digital video file? Why couldn't you then encode some information, let it evolve, reverse it, and get the original message back perfectly? Why do we always end up calling it just a quantum simulator or memory, not communication?
Because that if is the killer. Maintaining that perfect coherence, that perfect isolation, especially in anything complex, is practically impossible. The system can act like a fantastic quantum memory, yes. It can replay its own internal dance moves, if you like, but the instant you try to link that internal dance to the outside world, the moment you try to send a message across time, the universe basically slams the door shut. Decoherence, entropy, they kick in immediately and destroy that perfect reversal. And MRI, remember, is working with warm, wet, biological tissue. It's macroscopic, it's thermal, it's pretty much the opposite of a perfectly isolated quantum system. So while it uses the echo trick, any hope of actual communication across real space-time is just, well, it's forbidden by the fundamental rules of the universe.
Okay, so we've seen the math allows for a kind of reversal, and we can even simulate it inside the machine locally. Let's zoom out now. The cosmic rules, as you call them. If the equations are time-symmetric, why can't we actually send information through time? What are those fundamental barriers you mentioned, too?
Yes, two absolutely fundamental laws that lock time's arrow firmly in the forward direction, making real-time travel or backward communication impossible as far as all current physics understands. First, and maybe the most famous one, thermodynamics. Specifically, the second law. True time reversal on a macroscopic scale would mean decreasing entropy globally. It would mean the universe getting more ordered overall. That just doesn't happen. It violates the second law. So while your little 180-degree pulse performs a neat trick on the spin phases inside the sample,
The magnet is humming, the computer's running, the patient is breathing, the room is radiating heat.
exactly. The rest of the universe, including the MRI machine itself, is churning forward, relentlessly increasing the total entropy. Any tiny local reversal is completely overwhelmed.
Okay, thermodynamics. That's barrier number one. What's the second?
The second is equally profound. Causality, as enforced by Einstein's relativity. For information to travel backward in time, or even just to arrive somewhere faster than light could get it there, it would have to somehow appear outside its own light cone. The light cone is basically the boundary in space-time defining where something can possibly have an influence or be influenced from. Sending a message to the past is equivalent to faster-than-light communication.
And relativity says absolutely no to faster-than-light travel or signaling. That would break causality, cause could happen after effect, leading to all sorts of paradoxes.
Precisely. And there's no wiggle room there in standard physics. Are there speculative theories about wormholes or exotic physics? Sure, but they remain highly theoretical. The crucial point is that MRI experiments operate entirely within standard, well-understood physics. 3 dimensions of space, 1 of time. We're not accessing anything exotic by flipping spins. It's a manipulation within space-time, not of space-time.
That really nails it down. So the experiment doesn't break physics, it actually confirms the limits of physics we already rely on.
It does, but I think it does so in a really elegant way. Okay, so we can't build a time machine this way. The dream is off the table. But what the science does show us is this incredible boundary line where Reversible quantum rules meet the irreversible macroscopic world, and that is scientifically super valuable.
And it's something you can actually explore hands-on, apparently. The sources we looked at mention a practical goal, building a kind of educational demonstrator using a low-field NMR kit, not for time travel, but for learning.
Exactly right. You can actually assemble a small-scale version of this. You need a reasonably stable magnet. It doesn't have to be superconducting like in an MRI. Some specialized radio frequency electronics to generate those precise 90 and 180-degree pulses, a simple sample like water or oil, and some way to visualize the signal. It basically becomes a desktop model showing the core physics principles that operate inside a giant, expensive MRI machine.
So what would a student or researcher actually see or learn from playing with this kind of setup?
They get to see it happen in real time. They can directly observe how you can manipulate the spin phases to create that echo, how you can momentarily reverse the dephasing. But they also see very clearly how that echo signal decays over time, how T relaxation and imperfections inevitably cause the signal strength to drop, how decoherence, that interaction with the environment, always wins in the end. It lets you directly watch why the math says reversible, but the physical reality says irreversible. When you look at the whole picture, you see the memory fade.
Okay, so that really crystallizes the main point, I think. MRI spin echo is this beautiful demonstration that, yes, the fundamental laws of quantum mechanics allow for a reversible evolution in theory. But the real world, the macroscopic world we live in, is governed by decoherence, by energy loss, TRO, by entropy, and by the strict causal rules of relativity. And those forces together lock time's arrow pointing firmly forward. The echo remembers a past state of order, but it's not a gateway to the past.
Perfectly put. Spin echoes, Loschmidt echoes, they are powerful confirmations that quantum dynamics are time reversible at their core. But the universe's overall thermodynamic trajectory and the structure of space-time itself make that reversibility a purely local internal phenomenon. It's like watching a movie run backward inside a sealed room. You can see it happening in there, but you can't send a message out from that reversed timeline.
It really lets you watch that boundary, doesn't it? That contest between mathematical possibility and physical reality. So here's something to think about. Imagine you could achieve perfect isolation. You somehow shield one tiny quantum system, just a few spins completely from the rest of the universe and all its entropic noise. How long could you genuinely maintain its perfect quantum memory, its perfect potential for reversal, before the inevitable influence of the macroscopic world seeped in and forced its arrow of time to point forward like everything else?